So up to now, we've just been talking about the division algorithm. And the division algorithm says if we have two integers, a and b, where b is strictly greater than 0, then we can decompose a into a product of something times b plus a remainder. Now, an important case of division occurs when the remainder is in fact 0. So when a can just be decomposed into a product of two things. So this leads us into the idea of divisibility. So let a and b be integers, and now we're going to relax the condition that b has to be strictly greater than 0. Now we're just going to say that b can't be 0. So it can be something negative, just not 0. We say that b divides a if a can be equal to, or it can be decomposed into a product of b times some integer c. So we say, or we can also say that b is a divisor of a, or that b is a factor of a. So by factor, we mean if a can be decomposed into a product of things, then each one of those products is a factor of a. So when we're writing this mathematically, the notation that we use is a divides b is written as a line b. And if b does not divide a, so again, if we use the division algorithm and then we find out that there is a remainder that's non-zero, then b does not divide a. So using the idea of divisibility, this leads us into the idea of the greatest common divisor. So let a and b be integers. In this case, both of them cannot be 0. Then the greatest common divisor, or the GCD for short, of a and b is the largest integer we'll call d that divides both a and b. So to say this in other words, d is the greatest common divisor of a and b, provided that two conditions hold true. The first condition is that d has to divide each one of them. So it has to divide a, has to divide b. So if again, by the division algorithm, if there was a remainder for either one of these, this wouldn't work. Remainder has to be 0. Now the second condition is, let's suppose there was another integer that also divided a and b. Well, what needs to be true is that integer can be as large but not larger than d. So c, in this case we'll call that second divisor, has to be less than or equal to d, because if it was greater than d, then I would have something else that also divided, which would be larger than my greatest common divisor, and that wouldn't make sense. So the greatest common divisor of a and b is usually denoted, well, we'll see this in two ways. Typically we'll see GCD in round brackets a and b, or if it's understood that I'm talking about the GCD, then we're just going to see the round brackets in a and b. So the next question is, well, if we want to find the greatest common divisor, how do we do that? Well, in order for us to do that, we're going to use the Euclidean algorithm. Now, before I get into the Euclidean algorithm, this whole algorithm is based upon one condition holding true. And let's jump to the whiteboard for the second. So the one condition that needs to hold true, or does in fact hold true, is that the GCD of two integers, we'll call them u and v, is equal to the GCD, so it has the same greatest common divisor as, now I'm going to take the second term, this v here, and I'm going to put it in the first. And I'm going to take u, I'm going to put it in the second, but I'm also going to change this. This is going to be u mod v. Now we haven't talked about mod, we'll talk about that in the second lesson, but for now, we just need to think of this as the remainder of u after dividing by v. That looks horrible, let's get rid of that. There we go, after dividing by v. So the greatest common divisor of two integers is exactly the same as the greatest common divisor of the second integer and what remains of the first integer once we divide it by the second. So now let's go back to the algorithm here. So Euclidean algorithm is if integers a and b, or if we have integers a and b, we obtain a sequence of quotients and remainders. So basically we're repeating the division algorithm. So what I'm going to do first is I'm going to divide b by a. So by the division algorithm, a is on my left-hand side, my dividend, my divisor is b, so I'm trying to find a q and an r naught. Now, how many times I have to perform the division algorithm? Well, there is a stop condition. That stop condition is when the remainder is equal to 0. So let's suppose the remainder was equal to 0 in this first line. Well, what does that mean? Well, if the remainder was equal to 0, that means b is a divisor of a. So b divides a, b also divides itself, so that would be the greatest common divisor. So b would be the greatest common divisor in this case. if the remainder was 0. Now, if the remainder is not 0, then again, we go back to the idea of the GCD of two integers is exactly the same as the GCD of the second integer and the remainder of the first integer after we divide it by v. Notice that's exactly how the algorithm is set up. So if the remainder is not 0 here, the divisor now becomes the dividend, and the remainder now becomes the divisor. And again, we perform this operation, we get a remainder R1. If this remainder is equal to 0, then that tells me that R0 divides B, and R0 is the greatest common divisor, which would then be the greatest common divisor from the step above based upon, again, the equality of GCDs. Now, if it's not, then I repeat the division algorithm again. My divisor becomes my dividend, my remainder becomes my divisor, and I keep repeating this until I hit my very last time where I end up with a remainder of 0. Then when I have the remainder of 0, again, this tells me that Rn does in fact divide Rn minus 1, so Rn would be my greatest common divisor. And that's exactly what we have here. So let's run through an example of this. So we want to find the GCD of 78 and 30, and using the Euclidean algorithm. So this repeated of the division algorithm. So going back to my whiteboard here, and this is exercise 3. And let's move this up a bit here so I have some space. All right, so we start off with the division algorithm taking 78 on one side, 30 is on the other side, and now I ask the question, well, how many times does 30 go into 78? Well, it goes twice. So 2 times 30 gives me 60. I'm not quite up to 78 just yet, so I need to add on an additional 18. Now notice the remainder is 18. It's not 0, so I repeat the process again. So I do the division algorithm. This time my divisor of the last was 30. That's going to be my dividend on this side. And my remainder of the last time was 18. That's going to be my divisor here. So I ask the question, how many times does 18 go into 30? Well, it goes once. So 1 times 18 is 18. What do I need to add to 18 to get up to 30? Well, I need to add 12. 12 is not equal to 0. Repeat the process again. So 18 on my left-hand side, 12 on my right-hand side. And I ask the questions, how many times does 12 go into 18? It goes once. So 1 times 12 is 12. How do we get up to 18? I'm going to add 6. 6 is not equal to 0. Again, repeat the process. So 12 equals 6. How many times does 6 go into 12? It goes twice. So there we go. So that means 6 divides 12. 6 divides 6. That is the greatest common divisor here, which means it's the greatest common divisor here, and here, and here. So the GCD of 78 and 30, or, and I could write this as just 78, 30, is 6.